It's nice to meet you. This project was something I did when I was in upper administration. And I went to a lot of meetings that were so boring. And I said, I think I'm going to write something about how I should research. And so I would outline those when they were talking about something that didn't have anything to do with me, and one thing led to the other. And the success surprised me. My favorite is I'm a friend in Italy, who's director of health statistics, and he says, my English is not good, but I mean what I'm saying. You have made my life better. Not my work, my life. A key thing about workflow is it makes life easier. Just as a simple example of it, have any of you lost documents or had a document but you don't know where it is? No? I used to, but now in really faint font, I put the name of the document. No one ever complains, so I never lose them. It's a trivial thing to do that just eliminates. It's workflow. Setting up things that make it so you can work more efficiently. Now, for my talk, I want to start with the broader context that has really exploded in the last decade. And you see the same movement that is involving different aspects, replication and reproduction. Basically, are the results robust? Do you trust the results that someone has published? Scientific integrity. Has someone done it the proper way so that those results can be trusted? Open science and transparency. You can't trust my results if you can't see my data and if I don't make the information available. So you will see this movement, which Wikipedia and BBC has referred to as the replication crisis, occurring in all kinds of contexts. The National Academy of Sciences now has a standing committee to look at these issues, clearly indicate that it's being taken seriously. Journals are starting to require that you submit your files and your scripts before the paper is reviewed or after it's accepted. Different funding agencies have new requirements on accessibility of data. Undergraduates at Haverford don't get their degree unless they put their thesis on Dataverse with reproducible results. Undergraduates can do it, so who would? Finally, the methods section in sociology is devoting their methods meeting to issues of replication and reproduction. Sociology has been further behind. And you should all study regularly the site called retractionwatch.com. They document the thousands of papers that are being retracted because the results cannot be reproduced. It really is useful to go there and explore it and see what's happening. Why was this retracted? It's a trivial coding error that a first-year student and intern staff could have detected, but the authors didn't notice, but once it was published, it was found immediately. Here's a paper, it was a retraction, it was an old paper. Some researchers at Stanford were trying to analyze the data to update it, and they discovered these. You know what those are? Those are the old 99s for missing data. The authors hadn't noticed them. Ironically, one of the authors was an expert in missing data imputation, but they never looked at the data. Another example, paper I really like, where Simon Chang, Brian Powell went through a paper that had great influence on policy, went to the Supreme Court as an amicus brief, and they found that decisions made in the coding process totally changed the results. That's a difference, more of judgment calls perhaps, but it shows with open science you have different possibilities. Some recent retractions, the author wrote, a reanalysis of the data led to revised findings that do not replicate the results of the original paper. I think that paper was on one of these quick sites, and it was retracted within a week or so. The first person who looked at it said, wait a minute, and it came back. And criminal justice, someone sent an email under the name John Smith that said, data irregularities and requests for data arrived on Sunday morning. How do you like that for your week? It led to 5 retractions. A whole body of research disappeared because with the data, results were not reproducible. It's not just in the social sciences. A very interesting example recently just came out on the 3rd of January. A Nobel laureate retracted a paper in Science, preeminent science journal. Results were not reproducible and some data was missing. I'm totally bummed to announce that we have retracted last year's paper. The work has not been reproduced. It's painful to admit, but important to do so. I apologize to all. I was a bit busy when this was submitted and did not do my job well. What's so fascinating about this was the immediate acknowledgement of the problem. It points to the fact that when you get busy, you get sloppy. There's flat-out acknowledgement, and the response was positive, that this is what you need to do. Mistakes are going to happen. Now, as we're thinking about this process of assessing published findings, it's useful to think of different ways this occurs. And the terminology in the literature is all over the place, but this seems to be a consensus that's emerging. You have the original methods and alternative methods. You do exactly what I did as one. Alternative, you try a different methodology, you add random intercepts or something to see if the results hold up under alternative methodologies. The original data or the new. Exact reproduction is original data, original methods get the same results. The second part of my talk today is about you using your data and your methods and getting your answers. The simplest task that's out there. Robust reproduction is seen if the results hold up for more extensive or robust analyses. Replication is getting different data, collecting new data, or using a different data set to see whether your results are sustained. And generalization is when your findings hold up in other data sets, even with alternative methodologies. None of these are absolutes. There's kind of a continuum among all of these. And the results can vary in different ways. Ideally, the results are confirmed with the original data. Someone gets new data, and results are also confirmed. That's the scientific idea. Sometimes the results are confirmed with new data, even though they're disputed in the original data. There's some famous stories of this in the history of science. There was careless research. The wrong data was deposited. They wrote down what they did wrong, but it turned out that they were right. Sometimes you get contradictory findings. It just doesn't hold up in the new data set. If things have a temporality so that results don't hold now, that can happen. Or I can't get it with your data and I can't get it with my data. Maybe you're incompetent, or maybe you're committing fraud. So there's a lot of ways in which things can fail. Now, here I want to go through a list of these, and references will be at the very end of the talk. Why? Well, your new data theory and methods may not confirm the old. That's how history progresses. Newton was wrong, but it was replaced with new research. Fraud. The authors deceived the audience. That's fairly rare in science. Particularism in the review process, that may be actually more common, where the review process is not assessing the results scientifically. The incomplete documentation, you don't describe precisely what you did, so there's no way I can reproduce it. The concept that Polanyi introduced of tacit knowledge, it's very hard to do somebody else's work because they know things that are so second nature they forget to tell you. And the history of science is filled with examples. Tacit knowledge that was missing from the discussion. Sloppy science. You made a mistake putting the data together. You recoded missing into being divorced. I'm not likely to make that mistake in my own data, so I'm not going to get you results. I used methods that are inappropriate for the data. You also have something that's received a lot of attention. Psychology in particular has spent a lot of time talking about these things. It's what I refer to as data-driven model. That is when you use data to choose a model that you test with the same data. So stepwise regression would be one example. It's referred to as p-hacking, post-hypothesis, or post-data analysis, hypothesis construction. I look at my data, these are significant, I'm hypothesizing they're different, they are. A monkey can do this. Okay. Stepwise regression is fine, but you pretend this is the theory you hypothesized. You don't say this is a result of stepwise regression. Subgroup analysis, you make 20 comparisons among groups. One of them is significant, that's the only one you report. Well, you're not going to replicate. The reason this doesn't work is classical statistical inference says the null hypothesis is true. With random samples, you're going to be in the tail 5% of the time. This is what we would expect if the hypothesis is true. if you repeat it with 20 samples and nothing is happening, what's likely to be the case? In one of the samples, it's going to be significant. This is what we would expect. If only this sample is published after looking at the other 20, you're not going to be able to reproduce it. The classic example is that you test the effect of jelly beans on cancer. You use 20 different colors of jelly beans. Well, in one of them you find an effect and say, red jelly beans cure cancer. Well, it's a silly example, but that's what it means when you have data-driven hypothesis construction. You have publication bias. This is the notion that an incorrect effect, that is, that something happened, is more interesting in general than a correct lack of an effect. We're more anxious to publish something happened. This variable affects the outcome. To give you an example of how this occurs, is I took 5 random samples from the same data set, and I ran stepwise regression in the 4 samples. In one, there's a strong suppressing effect of being a female in diabetes, but only in one of them. Well, I'm publishing that one. This is publication bias. It wasn't theory. It wasn't saying, I think gender is important. It's like, wow, my data showed it. So it's not going to be replicable, but it will be reproducible. You have my data, you can get the same answer. What can authors do to improve this? One notion that is seen in a variety of different ways is pre-publication robustness checks. One of them that I like is by Young and Bolstein at Social Methods and Research a few years ago. The idea is a simple one. So when you're modeling, you've got an outcome. In this case, they were looking at estimates of the people that migrate from a state due to the tax rate. So this was a big political discussion. If you raise the rates, will people leave the state? Now, when you're modeling, there's a number of variables that you think are critical, and then most people have a bunch of other variables you might or might not include. Those controls, right? If you had that, it's not obvious how many, but you pick some, and there's a variety that you choose. What they're arguing is you ought to run the model using all combinations of those variables. In this case, they did it, and they ran 24,576 models, and they plot the effects across all those models. Here's no effect. Here's the effect they reported, and it shows that, boy, in most of the models, you're not going to find much of an effect. What they argue is this should be included in every paper in an appendix for the effects that are considered critical, so you understand how sensitive it is to model specification. There's other examples in the literature that in one of the references I'll talk about, you'll see. Another proposal is to start using standards imposed by journals, societies, organizations for what's reported. Have public archives where you deposit data and scripts. You report the information, and it's assumed that it'll be there. The use of standard documentation for how you describe your sample, data collection, variable construction, model selection. In a class with 50 students where everyone was asked to go out and find a paper that had data set in the public domain, almost none of them could tell how the author created the variables or collected the sample, determined the sample from what was published. And I didn't allow them to annoy the authors. And they had to try all kinds of things to see if they could get close. So the idea is, what if we set up standard expectations? Here's what you need to report, and include either on an online appendix or someplace, so you know exactly what was being done. Another idea is to use full evidence from prior research. Have study registries. So whenever you get a finding, it goes to a registry. So let's say I'm looking at the effect of gender on the scientific career. I can put this into a registry, and all the studies that are out there come up, so I'm sure that I've incorporated the past research. Or to extend it, things like meta-analysis, where you give me your data set, you give me yours, they're similar, I put them together and do a single analysis that combines all of those kinds of results. The idea being that you fully utilize what the scientific community knows about the research, which gives you a sense of what you might expect what you might not expect. Pre-registration of analyses is the idea that you ought to say what you're going to do before you do it. In high-energy nuclear physics, my squash partner in graduate school was a high-energy nuclear physicist, and he said, we have to tell them exactly what experiments we're going to run and what we expect to get in the proposal before they give us money. That was pre-registration. Then you had to show them if it worked. So some biosciences do the same. If you collect this data, you have to tell us precisely what analyses you are committed to running, and then you have to report those. You can do other things, but you at least have to do what you said you're interested in. I was talking to someone in the audience from clinical psychology saying that's something that's being done there, that people pre-register what analyses they're proposing for the papers. Is that close to? Yeah, it's
so
an idea.
We're encouraging people to do that more and more. Making it standard practice for ourselves.
Yeah, it's a great idea. It's also a great way to plan how to write a paper. Do the pre-registration for no one else yourself before you start your analysis, a point I'll come back to later. The idea is it keeps you on track, and then you make sure you see how your insights led to conclusions that weren't driven by the data itself that led you to change your hypothesis in ways that you may have never thought of. Okay. And related to this is a notion that maybe the review process should be modified so the scientist has a design, the review of the paper occurs there. Not after it's written, but when you propose what the paper is going to do. Then you make the decisions. It's a way to get around publication bias. So all of these are notions that are being considered and discussed in the literature. In the reference book with Jeremy Fries, Christensen, Miguel, I think they have a really great review of all of these different things. So you pick up the reference. Science has been filled with discussions of these crises. They made it on the news. You find them in BBC. You find it in the New York Times. You find it on any place you go. You find this. And there's claims of fake science. There's a great case of people submitted the same paper to 3 journals, and it was all nonsense, and it was published in 2 of them. And it was written by 2 characters from The Simpsons. But it got published, and all of these embarrassments. And so Christy Oshwander wrote this article called Science Isn't Broken. She said she took months investigating failures in science, and she concluded, the state of our science is strong, but it's plagued by a universal problem. Science is hard. It's really effing hard. That was her conclusion. Yeah, some of these things occurred, but if we're going to rely on science as a mean for reaching the truth, and it's still the best tool we have, it's important that we understand and respect just how difficult it is to get rigorous results. And I think that's the takeaway. It is really hard to get rigorous results, and we need to be aware of it. There are going to be failures just like the Nobel laureate. Mistakes will happen, but you want to try to minimize those. This is where workflow comes in. The workflow book, when I wrote it, was in response to all the years working with graduate students, teaching classes, consulting, collaborating, and saying, oh, there's some things I'd like to kind of get them organized. There's certain things that bothered me. I wanted to fill in the blanks, kind of put it all on the piece. And eventually it led to the book. And it talked about reproducibility as the primary criteria, but it also focuses on the issue, if you will, of getting things done. You'd like to get the right answers efficiently. And so it's a set of procedures to efficiently and accurately produce results that are reproducible. It is workflow. It's a concept that you will see in a variety of different contexts. Supercomputing uses the term of workflow. What are the steps? What are the procedures that you use? It encompasses everything you do in the research process. Planning the research, constructing variables, documenting work, revising analyses, importing data, analyzing it, presenting results, preserving the files. It is the entire process. And the key is the coordination. You will not have an effective workflow unless it's coordinated. It won't be coordinated unless it's planned. I want to focus on talking about reproducible results is what I refer to simply as author reproduction. Not me giving you my data and seeing if you can get the answers. I want to see if I can get the same answers using my data. Well, seems pretty easy. It's not as easy as it looks. So, why is it harder than most people think? You try to tell someone you're studying how to get the same answer twice, they look at you like you must be dull. It's like, really? All you have to do is do it again. Why is it so hard? Well, one reason is research involves lots of decisions. And trivial decisions, important decisions, I'm going to divide the variable at 2. No, I think I'll divide it at 3. I'm going to top code this. I mean, you've got dozens and dozens and dozens of decisions. If you only made 20 decisions, there'd be a million different ways you could proceed through your research. So here's where you start. You've got to choose here. You choose one, you go a different direction. To get your answers, you follow that path to the published result. If you don't know what you did, you've got to look at all the paths. Some years ago, Paul Alice and I did a paper, then he did a paper using it. I wanted to write another paper using the analysis he did, and we couldn't quite get the exact answers from his paper. It drove us crazy. He had had a massive computer failure, lost one of the script files. We eventually said, we're close, we just can't get it. We gave the data to someone else later. He said, great, I got exactly the same result. He picked the right path first time. It was a miracle. But Paul and I never were able to. We lost track of the steps. Now, if the workflow is how you navigate the path, how do you decide how to do this? It might be planned. So before you start your research, you have a plan that covers the whole process. My experience outside of the lab sciences, that doesn't happen very often. In the lab sciences, it's very, very precise. The lab manager gets you your funding taken away if you don't follow those. Social sciences, not very often. Might be ad hoc. You try something, if it works, great. If it doesn't work, you fix. Most people, it's reactionary. I didn't really back up my data sets, but then I lost an important file, so now I'm backing up my data sets. It's problems occur and you fix them. So how do you decide if your workflow is good enough? This is the test I give in a class on reproducible results in statistics. Think of a project completed a year ago. Ask people to go out, find something you did a year ago. How long will it take you to find the scripts in the data set, rerun the scripts and get identical results, change one variable, rerun the analysis, and update your paper? It should take an hour. It's a reasonable standard. Now, most people can't do that with something they did last week, in my experience, from these students, unless they're just, Indiana students. I know Kentucky has views about that, but they can't. With collaborations, I've encountered the problems. So you worry about the workflow to accomplish these things. It's essential for getting results that are reproducible. Thinking about how you're doing your work. It prevents errors of two types. And as you hear things, particularly in the second half, that seem pretty overly complex, the workflow prevents two kinds of errors. These little annoying errors you probably catch. Oh, it's annoying, I got the variable name wrong, I'll fix it and go back. And black swans. These are things you really expect you'll never see, but when it happens, it's a devastating retraction. You're trying to prevent really bad things happening. Mistakes that shouldn't happen, but they do happen. It will make errors easier to find. You will make lots of errors, but your workflow should help you find them and make it easier to fix them. It's going to save you time. Many of the steps may seem to be slowing you down. It saves you time in the whole project. Most time, in my experience, occurs going back to fix problems, not in doing the documentation or the details along the process. People in general feel more comfortable fixing a problem when they have to than so-called wasting their time in the process, saying, well, it's probably not going to be needed. So it's a set of procedures that you impose all the time. Why does it matter? Most painful case I've seen, a student wrote his dissertation in 8 months. Analysis right up during the defense, some numbers had changed. The question was, how did they change? He couldn't explain it. He couldn't show where he got them. It took him 18 months to work backwards to get the results that justified the dissertation that was already written. He almost lost his job. He just lost track of how he got his results. And you can't give a degree when you say, I got these results, but I don't know where they came from. And it was simple. There wasn't anything wrong. He reproduced them, but he lost track completely. I was invited to collaborate on a paper to add some methods. Got the paper. They gave me one script file. I ran it. None of the numbers in the papers were in the output. So somewhere along the line, the right file disappeared. Everything had to start over. Conflicting results from the same data in a project goes on. The research assistant said, oh, the data sets are exactly the same except for the married variable. For me, they're not exactly the same because we were getting different results on the married variable. Someone changed it, kept the variable, the name of the data set the same, and didn't tell anyone. Wrote a report. Last time I was here, it was for the report at the National Academy. It took months to deal with the fact that the programmer didn't grab the right variable. It was similar but the wrong one, and all the results were wrong. Colleagues spent 2 weeks trying to reproduce his results. He thought he was going to have a retraction from the article that got him tenure. It turned out to be they were reproducible, but he'd lost track how he got them until he could resurrect it. It was the worst 2 weeks of his life to find out because his results were being challenged, not as like they're wrong, but I'm doing a new paper based on yours and I need to get your data. That's what the problem was. And output like this. See any problem with the table on the top? Definitely, definitely. So definitely we don't know which is definitely agree and which is definitely disagree. I was in a meeting where there were 3 PhDs arguing which end was agree and which was disagree. Because the labels were truncated. This happens oftentimes. Or these wonderful variable labels, where all the useful information was on the right. How important is it to go to, turn to? Well, you're going to grab the wrong variable almost certainly, and you'll never notice it. These things happen all the time. So as you're thinking of your workflow, this is the man you use as your inspiration. What I call ironical optimism. This is Mr. Staff, girl. It's on the rockets. Went from 0 to 1,000 and back in 3 seconds. The time of great stuff. I was fine, only blind for a few days. And his famous statement, he managed the lab where all this research was done. The universal aptitude for ineptitude makes any human accomplishment an incredible miracle. And he was an optimist. He says, you guys are going to mess it up, particularly you, and I know you will. Get over it. That happens. So we work together. You check her work, I check my work, you check. You assume it is going to go wrong. And so this was the motto that ran the most dangerous experiments on human subjects ever, and no one was ever injured. And this was his philosophy going forward. So let's talk about how this works in a research project. This is kind of how I see research proceed. You know, you've got an idea that inspires you. You get the data set. You find that the data set doesn't allow you to do what you want. You go back to the idea. You get some other data. You do analysis. The analysis suggests you need other data. You go here. You do a presentation. You come back here. And you kind of move among all of those different steps, back and forth, depending on the paper and the type of work you're doing. All along these different stages, there's various tasks. These are discrete things that need to be done. Okay, we need to construct scales of functional limitations. Okay, that's a task. That's part of the data. Each part of this has different tasks that need to be accomplished. To complete the task, you go through a variety of activities. You make a plan. How are you going to get the work done? You get organized, you get the pieces together, you choose the names, you do various things that are more organizational. You do the computation, you document what you did,
You kind of keep working through these. We go through all of these steps. Which step do people like the most? Which activity do you like the most? Computing. How many of you like documentation? Because I got a job for you. Nobody likes to document. Okay. So with all of these, you have to back up your files. The file will be lost at the worst time. A hose will be left on in the room above your computer. This has actually happened. Your partner will delete all of your files the day before court. It did happen. Your computer and backups will be stolen when you move. This is so prevalent that PhD Comics has the 4 stages of data loss. I did not just erase my data, stick a piece of crap, where's my data, find the infection, and then acceptance. Never going to graduate. Indeed, the student in Indiana dropped out. Data loss. It will happen. So what do you do to avoid data loss that causes retractions? You preserve the file and their meaning that allow you to reproduce your results. Increasingly, that's an expectation. On retractionwatch.com, a number of the retractions are simply, they can't give us the data. The journal's taking back the paper. The rule is 3-2-1. You make 3 copies on 2 media, on 2 different kinds of devices. One's the cloud, one's a hard drive. Those would be 2 different media, with 1 copy located off-site. That's a simple basic rule. There's a lot on backing up, and I'm not going to go into details. It's something to take very seriously. But that's a key rule to think of those kind of aspects. Have equipment that can read the media. The devices become obsolete, migrate files to the media. On a project, we had the backup. We needed a variable on it. It cost us $2,000 to pay a place that still had a tape drive that could read our backup tape. We had the tape, but no one could read it anymore. You need formats you can read. Colleagues sent me this. These files were saved 6 years ago in the Gauss FMT file format. Nothing can read them anymore. The format just disappeared, and they were really stuck. We had to go into the binary files and figure out what the data had to be. It was horrible. Planning. The best advice on planning is from Michael Faraday, one of the great scientists of all times. He was such a great scientist that that's the portrait Einstein had above his desk. Faraday was his hero. And Faraday in his laboratory had a sign, a little article in the History of Science about it. It said, work, finish, publish. And as you're planning, you want to keep those things in mind. Working doesn't do you any good in science unless you finish. And finishing is no good if you don't get published. So your plan is involved on staying on track, finishing the project, and getting the results published. The plan is what gets you there for the most part. In my mind, planning is probably the most important thing people can do to their workflow to increase their productivity. It's easy to spend a day doing something that's not critical, and that day would have kept you from doing it in maybe half an hour by making a plan. So that plan. Most people on doing research compute every day. And after the dissertation proposal, they don't plan for months. That's probably backwards. You want to reserve uninterrupted time to plan. This is one of the things I have to make myself do. So typically, I travel without a laptop, because with a laptop, I can find more interesting things to do. So I carry a notebook or an iPad, and I do my planning. I review the projects, and I make the plan, where there's nothing that's getting in the way. I get to the airport early, so there's no stress. I sit in a corner, and I kind of review the projects and make my plans. Because if I'm back at the office, I'm going to start checking this variable, check this reprint, do this thing. So it's something I find really, really useful to do. You plan all of the different pieces. The timeline. When do you expect what to be finished? What do you want to publish where? In what order? What's the sequences of papers? Who's going to do what? When? In collaborations, that question is often not asked. Who is going to do it by what date? And make it explicit. How are you going to do documentation? How are things organized? What are your names and labels? Do you plan them so that they're easy to read, or do you say, I am not going to go to go to? I mean, that clearly wasn't planned, but it's what we got. What files to preserve? Everything should be planned to some degree or the other, so it's following along. And the plans, I find, need to work on different levels. The grand plan is something I have to make sure I do 3 times a year. What are the things I want to be doing? I look back the last 3 months or 4 months, I look forward and say, okay, am I on track? Is this a good project? Should I abandon it? Do I want to change it? Am I too bored with it to do the work? But during the period, I'm just doing the work. Then the big plan, looking at my project, what are the big goals? What are the objectives? What are the limitations of the project? Kind of saying, what do I want this project to accomplish? It's really hard for me oftentimes to have a paper where I can say, here's what I want it to do, and in 1 sentence describe it. That really helps me stay on track and write more effective papers. Plans in the middle is where a lot of people get stuck. Where you look at kind of the small things, oh, I need to recode a bunch of variables, and you think about all of that. And then you get it all done and say, well, I didn't really need those variables. But you got caught up in that intermediate stage rather than the bigger question of what needed to be done. The example was a dissertation proposal that was a great proposal, and they forgot to check whether the indicators that were needed were there. All had to be started over. It's the planning part, looking at those pieces. And then the nitty-gritty details. You know, I want to do a random intercept model and such a model. Do you have software that can do it? If not, better master it before you get there. You know, those are technical details you need, but they're kind of at the end once you get there. Organizing is the low-hanging fruit, meaning, man, it is the quickest return on your dollar to get organized. Now, let's see if people at Kentucky are honest. How many of you encountered you can't find a file and think you deleted it? Okay, me too. You have multiple files with the same name but different content. Yeah, you and co-authors are simultaneously editing different versions of a paper. That is just ugly and painful because you both know the other person had one. 2 authors mistakenly think they are analyzing the same data set, but they're different. And now you have to reconcile content. Yeah. You have multiple copies of the same reprint, but can't find any of them. How many of you have downloaded the same paper more than 4 times? Yeah. Boy, that's a good investment of time, isn't it? Now, is final report version 16 the final version? I gave this talk at ICPSR the other summer, and a student came up afterward and showed me her phone and said, urgent, don't analyze final.data, use last version.data for the presentation tomorrow. What comes next? You know, clearly these are silly mistakes on people that don't know what they're doing. It wouldn't be authors who published the wrong paper in a journal and had to retract the whole thing. Yeah, it happened. They, you know, it was accepted and they submitted the wrong document and it got published. And nobody noticed. Okay. Now, what's involved in organization? Really, I define it as you only need 2 things to be keeping going. You want to find things quickly and you want to avoid duplication. If you do those 2 things, you're in great shape. Think about your house. What is it about organization? It rewards consistency and uniformity. If you do it the same way, it works better. You do it the same every time. It's contagious, as is disorganization. I don't clean my desk at the end of the day. By the end of the week, I can't find anything. It just grows. And it takes maintenance to overcome entropy. Things will start going awry. There will be crises. Things will get out of there. Files are the biggest issue for most people. I did a quick check before I came here, and there were over 2 million files on my hard drive. So most of you have that many, and it's going to get worse with time. It's easier to create a file than to find a file. It's easier to find a file than to know what's in a file, and it's easy to create a lot of files. That's the dilemma. the trick is digital asset management. I learned a whole lot about this as a photographer, where I spent more time looking for the photo than printing it, because I had thousands and thousands of them, and I read this book called The Damn Book, Digital Asset Management for Photography. So the term is DAM, but it's digital asset management. And the key is that a file's name and directory location document its content. That's the key. Final doesn't tell you much because it's not final, and you got lots of files called final. We use a directory structure where every file belongs in exactly one place. To assess whether you're in good shape, think of any file you have and say, can I think of the one place it should always go, and every time that's where I put it? If not, your directory structure is causing you difficulty. So let's think about naming. Here's how I named the paper with Sarah Steele. Groups, the date it was written, that's who wrote that draft. No way to get it confused. Who wrote that draft, when it was written. Sarah did a draft, SAM for her initials. No confusion. We never grabbed the wrong one. Piece of cake. Sarah didn't like to do this stuff, so she would post it in a file that was shared. I would then put the name in our format. It doesn't matter how you get it done, but there was never confusion as to which draft was next and which was the latest. Here's the name of one of my reprints. It used to be called that. Which one's easier? So you download a file, a paper, quickly rename it. It's way faster than downloading it again and again and again. And then put them all in the same place, and I'll tell you where to put those. You have a data set, final 1, final 2, final 3, final 4. Well, try something, groups, HRS, Health and Retirement Survey 1, 2. Man, I'm pretty sure which is the latest, what project it's associated with. Easy to keep track. I don't need much documentation. Here's a simple directory structure. Operating systems do a horrible job helping you organize files. They give you more specialized directories for entertainment, right? You've got movies, you've got pictures, you've got, what about research papers? What about classes? They're not there, so you have to impose it. So, to show, what's that? Those are files that aren't where they belong. If I put them there, they're in the right place. Just like a library. The to-shelf cart is the right place for that book because it's in the wrong place. So it's never floating around. Active, these are my active projects. The group different projects, everything for that project is in there. Maybe subdirectories. UK talk, all my files for this talk are right in there. Active on hold, I was working on this project. I decided I didn't want to. I moved it there so I knew I wasn't working on it. Just to clutter things up. Administrative things, whatever you have to do for administration, they get stuff there. Bookshelf, that's where I put all the PDFs I download. It eliminates duplication. I know where to find them. Done. Solves the problem. Shared, these are my Dropbox shared, Red Mason. Everyone I collaborate with has another folder here. They're not scattered all over, different names, easy to find them. Templates, these are sample documents. Anything I'm going to create multiple times, I put in there because that's a sample. I don't have to start over with formatting. Vault, this is an idea we'll get to in the second part. These are files that I will never change. This is a wonderful invention because you can forget about it. You're never going to change it. Like what? You have files for a research paper. You can never change them because if you do, you won't be able to get the same answers. So that's where they go. And I know never change anything in Vault. So this is just a really bare bones structure. At my class at ICP Sarah, we spend about 4 hours on setting up structures that are effective for working efficiently. Documentation. Nobody likes to write it, but everyone likes to have had it written. The trick for documentation, in my experience, is to write it today, revise it later, and use reinforcing modes. So this is the method that I've come to use. The script files tell you exactly what you did. Exactly what you did. Your research diary has your various notes, your timeline, did this, but it doesn't have to tell you the details of the script files, but it points to them. So if you have a question, you go to the script file to find out exactly what you did. Metadata is data about data, and your script file uses some of that metadata. Your data set has information in it. So when you save a data set, you can put metadata telling you where that data set came from, When you create a variable, you can add metadata about it. Variable labels are an example. So that metadata tells you things you don't have to put in your diary. What's the best way to tell what a variable is? Look at the variable label. If it's a good label, you don't need to put this in your diary. When you're writing, point to the script files that gave you your results. If you're presenting a result, what's the best way to confirm what you did? Point to the script that did it. And then you know exactly how you got those results. It uses a variable that you don't remember how you created. Look at the metadata in the data set. So by using these different forms, not as redundancies, but as independent sources that link to each other, documentation is pretty simple. Your documentation should be fairly short. The second part of the talk, we'll talk a little bit more about doing. My research diary is pretty simple. Here's a paper that Zach Kennedy and I did a little while ago. We were recreating a reproduction data set. Here's the script file. Here's what it did. It created this data set from this. Here's the next one. Analysis in the paper. Simple description of the data set used. Simple list. That's it. That's the entire diary. But it pointed to the script files that I knew exactly where they were located in the vault. So if I wanted any questions, I knew exactly where to go, and I didn't have to put a lot more details. I would add more to this if there were things that were unusual or peculiar, or that I wanted to be sure I remembered in the future. But it doesn't have to have a lot of details. Metadata, here's some examples. In Stata, you can embed all kinds of metadata. Different software lets you do it in different ways. Well, first thing I tell you how to add survey weights, because people get that screwed up all the time. So I embed it in the data set. So I don't have to tell people. Say, look at the notes, it'll tell you. Here's where the data came from, so I know the origins. Here's the name of the data set, and here's where the data set was created. So I'm pointing to the script that created that data set. If you say to me, I don't understand how you created this variable, I grab that script, I look at it, and I can tell you the answer in a couple minutes. So it's pointing to it. Variable names and labels, that describes those. Metadata about variables, here's a variable that was created. It's reverse coding of a source variable called sci.gov. We renamed it to add part 2. Here's the program that did it. This information lets me trace out exactly what I did very, very quickly. But it only works if I always do. If I can't count on it being there, then if I don't find it, I don't know what to do. So this part, you kind of set your rules for documentation, find a way to work, and proceed. When you're doing your computing, you use script files. Friends don't let friends point and click. You just don't do it. Everything's in a script, because otherwise you can't do it the same way unless you're in an environment that records the pointing and clicking, and that's not realistic. Okay, you work in script files. In the second part of the lecture, I'll talk about how you make those script files effective. The diary metadata and provenance tags point to the scripts that provide the exact documentation of what you did. The diary gives you justifications. If there's something subtle about what you're doing, you put it in the diary. It seems that this result may be incorrect, but according to so-and-so, this is commonly found using this type of data. And you put that in there in case someone ever has a question. Then when you're writing your paper, the best trick I discovered for writing papers and for revising them. Twice I have had papers that were accepted with no changes. I think it was a mistake. But of course, I wanted to make changes. But changing papers is difficult a lot of times because you have to know where every number came from. The solution for that, which I now use, is here's some results from a paper I did with Eliza Pavoka. So those came out of a script. Now, let's say I have to make revisions and I know it's going to affect those results. How do I know where I can make that correction? Well, using a hidden font. That's a font you can't see. It's in Word and you can do it in LaTeX. I put the name of the script file, I give it a number, so my script files have part 1, part 2, part 3, so I know exactly where to go. I ran it on that date. So if I want to know if that result has to change, I look at the hidden text and I know exactly which file I have to change. By doing this, Any result that's challenged, I can immediately pull out the script that created that result. I can say, oh, there was a typo. Grab the wrong number. That's all it is. Or I can say, no, it is right. Here's what we did. Okay. By doing this, it's incredibly easy to make revisions to a paper. So whenever I'm writing a paper, I put in something that's data-driven. I immediately put the name of the do file, the date, and who got those results, and I put it and make it a hidden file. Boom, that's it. And it is vastly simpler if your results are ever challenged. You can say, well, here's where the result came. Boom. So it's a really simple trick. Computing. This is the computer I use. We had 228 kilobyte of memory. 228. I remember when it came. We had a 360, went to 370. People were dancing in the street. It cost $1 million. The drives, 3 megabytes on every drive, and there were 3 of them. 9 megabytes at the same time. 7 years to get a PhD. Now, I just did a look. For $1,000, I can get 8 gigabytes of memory, 4 terabytes of storage, and the average time. I'm actually told it's longer than 7.6 years now in sociology. I don't think computing is the problem. So here's an experiment I'm asking the graduate school to let me do. I want to divide students randomly into 2 groups. The group I don't like are allowed to compute anytime they want. The students I like only get to compute 12 hours a week. Who finishes first? I'll bet in the green group every time. In my experience, more problems are caused by computing too much than too little. There is a temptation to compute. I have to resist it all the time. I suspect you do. Writing scripts and computing is the perfect example of intermittent positive and negative reinforcement. I do it all day. So in the second, I'm going to skip this. In the second part, we're going to talk about this workflow for how to compute more efficiently. Okay? Data cleaning is an issue in your workflow that should take you more time than your data analysis. Too often people clean their data sets or variables when they get a result that seems anomalous or they see a problem. What does that do? It means you only find things that look wrong. Wrong things that look right are okay. You want to clean your variables very, very carefully. I like cleaning data sets because I view it like exploring antiques in my mother's attic. Wow, this is really neat. I never saw that. I don't view it as cleaning out a dirty old attic. You explore the data, you think about it, you look for it. So let's take some examples. Here, the correlation is 0.34. The range of the data is right, but that triangle tells you a whole lot. Most people are moving down in prestige. The correlation doesn't tell you that. The regression won't tell you that either. What's this? Oh, that's a person who had one paper at a low prestige university that was incredibly good, and he got a great job. And most people end up in institutions that don't have graduate programs. You can't see that in the descriptive statistics, but if you plot it, you see it. This is the graph that would have prevented thousands of dollars wasted, trips to Washington, D.C. But the data analyst, who was an econometrician who was very well trained, never looked at the distributions and didn't notice that nobody is enrolled in graduate school for 25 years. This is elapsed time. He said it was enrolled time, and it skewed all the results. Many retractions can be caught. The one we started with, this is what they had to look at, a two-way table between the source variable and the recode. And they would suddenly say, 47 missing cases are now divorced. That can't be right. It's a simple task. Spend lots of time on data cleaning. I like to use graphs, scatter plots, jittering, look at it different ways. As you go, that's when I start writing insights about the data, thoughts about it, things I want to remember. But take your time. Lots of retractions are data problems. Another thing I encourage you to do is think carefully about missing data. We spend a lot of time talking about multiple imputation, maximum likelihood, full information imputation, all kinds of things. But not all missing data is missing. Certainly not in that way. Here's an example on a survey at the Kinsey Institute. The variable time married had the most missing data. People would tell you in a public forum how many affairs they had had, but not how long they were married. Does that make sense to you? It didn't to me. So when I looked into it, the data collection organization created the variable time married by adding years and months, which were 2 questions. People who were married a long time didn't put in months. People who had just gotten married didn't put in years. Those were coded as missing because they expected you to put 0, not skip it. So when you added them, it was missing. A lot of checks. All the missing data went away. We did checks to make sure that that made sense, that there wasn't some artifact. Well, is that better than multiple imputation? Well, I'm pretty sure the data is not missing completely. None of those other methods are going to work. A lot of missing data, in my experience, isn't missing, but can be inferred from other information in the survey. So take lots of time looking at your missing data. On data analysis, before you start, do something akin to pre-registration, is my advice. You want to plan your analysis to prevent running analyses that you don't need. I do that if I'm not careful. Something catches my interest and I run something else, and I'm off and running and doing all kinds of things. You forget things that are more important. If you write the abstract before you write the paper, it keeps you on track. Plus, you don't have to write it later. Secondly, I create dummy tables and figures for everything I'm expecting to do. I just sketch them out quickly, but it doesn't take a while. Each one gets another sheet of paper. Then I add notes to it as I'm thinking, and it kind of keeps me on track. I don't get to the end of the analysis and say, oh, I forgot that table. I'm getting into sidetracks. When I find things that I didn't expect that suggest other analyses, I have another script file open that says other things to pursue. I don't want to forget those because sometimes those are really valuable. But I want to make sure I finish what I had in mind. The best example of this is this amazing book by Blau and Duncan. It came out in 1967. It changed the way stratification research was done. It brought together Blau, a theorist, Duncan, a data analyst, a demographer. They were asked to indicate all the data analysis they wanted for the book. 3 months later, they got the output, and that was it. This would be like me saying, tell me what you want for analysis in your dissertation. I'll give it to you in 3 months, then go write it. It's the best book in the series. I mean, it's a brilliant book. They did pre-registration, and it came out as a brilliant piece of research. So it is possible. Conducting analysis. Use script files. Do not create variables in the script files is my advice. We'll talk about that in the second part. And create a replication package, or a reproduction package would be better. As you're writing, start creating the scripts and the data set necessary to reproduce all your results. Do them as you're working. Don't wait till you're all done and work backwards. So you're doing a bunch of scripts and say, okay, this is essential. I'll grab that and stick it in my reproduction script. So that when you're done, you have a second set of script files that only reproduce the results from your paper. It does a couple of things. One, it gives you another chance to make sure everything is right. You review it, you coordinate it, you document it, you double check that all the answers are right. Recently, I did this for a paper and we found one mistake that we would have had to make a correction and a rat after the paper after it was published, but we found it doing the replication package. Secondly, if you do this before you send it out for review, when the reviewers want changes, it's much easier to do it because all of the things you need are in that replication package. You don't have to go through the hundreds of files you had before. Then, if the journal requires it, it's already written. You're close to doing it. So it's really a handy item. Now, changing your workflow. It's not easy. The younger you are, the easier it is. That's the good news. How do you decide what to do? You need to assess your workflow. List the problems you notice in your work. It's a great exercise. Just make lists. What things do you find are annoying, time-consuming, lead to problems, are frustrating, bothering? Just make a list. I forget which file is most recent. I don't remember how a variable was created, and I have to double check. Revisions take me a really long time. Just make a list. Replicate a paper you've already written or an assignment for a class. Keep track of what problems you have, what worked, what didn't work. Make some priorities. Which problems affect reproducibility? Which cause errors? Which waste the most time? So you have priorities of what you want to do. Then, how do you decide how you want to work? You have to have some priorities. First of all, reproducible. If your procedure doesn't let you reproduce your result, you shouldn't use it. Period. You want it to be accurate. No one wants to reproduce the wrong answer. You want to be efficient so that you can finish the work to have a publication. So what things affect your efficiency? Then there's other criteria. You want things to be coordinated. If the different parts of your workflow work together, they're going to be more efficient. They're going to be easier for you to use. You want them to be standardized. You don't want to name data sets one way and have a different structure for papers and then other things. The more uniform it is, the easier it's going to be to stick with it. You don't want to think about workflow. You just want to work. You don't want to debate. As a surgeon, you don't want the surgeon to say, gee, I'm wondering how I should make this incision. Well, there's a lot of ways. You want them to come in knowing what they're going to do and not spend their time thinking about those kinds of decisions. It's the same principle. You want it to be automated. If you're doing a lot of data analysis, learn how to do some stata programming or R programming, some more advanced techniques that may save you time. But only if you're doing a lot and if that's something that you would do. Otherwise, it's a waste of time. You want methods that are scalable so that they'll work for a paper for a class, for a research note, for a dissertation, or a research paper. You don't want to start over every project because, oh, this is bigger, I have to do things differently. These are ideas. They also have to be usable. If they're too complicated, you won't remember how to do them and you'll give up. They need to be congenial to the way you like to work. One of my collaborators, on certain things we did them differently because what she did, I didn't like working that way. What I did, she didn't like learning new software. But it worked fine on those tasks. And it meant we would do the things that we wanted to do and transferable. You want to be able to give your results to other people so they can follow. Terry White, a research associate, used to say, this is the hit by the bus criteria. If you got hit by a bus, could someone figure out what you're doing? You really want to have that in mind unless you're saying, let it all disappear. Then, whose workflow should you use? Now, sadly, I called the book The Workflow of Data Analysis. I should say arrogantly, but sadly. It should have been a workflow. Because there's lots of ways you can do this. Perfection is not something you want in your workflow. You're not going to have a perfect workflow. But you want it to be good enough. That may be the optimal workflow. To prevent the most egregious things, to address the greatest problems. As you choose a workflow, do you want to spend time looking for something better? So I make a proposal. There's probably something better. Is that what you want to spend your time doing? And testing it and revising it. Do you want to make the mistakes I made? I could do a 2-day lecture on mistakes I have made and how I had to address it. So think about it. Now, should you say, I'm changing the way I'm going to work? No, not everything. I want to go back to old research and redo it. But let's say you're starting a new paper. Yeah, try your new methods and follow them through. And force yourself to stick with it. Keep in mind something from a book I read in high school, I think. It was Tennis for Your Future by Vic Braden, one of the great coaches of pros. He had this line, Vic says, how does that feel? He'd show you how to do something. Awful. Remember that awful. It'll make you famous. The idea is learning new things can be painful, awful. Stick with the new procedures before they become routine. Every time an iPhone comes out with a new iOS, people say, it's awful, it's the worst thing I've ever seen. And 2 weeks later, I'm saying, hey, isn't this great? Initially, it feels awkward and difficult. It's unnatural. Don't bounce back and forth. Make some decisions, stick with them, and move forward. Because if you have 2 workflows, you're in worse shape than when you start. It's just too hard. Finish what you change. If you decide you're going to rearrange your directory structure, finish it. Don't do most of it, or you've got a bigger mess than when you started. Take it gradually. Don't do it under a deadline. Make priorities, get periods and say, okay, I'm going to work on this aspect, I'm going to learn this skill, and build it into my workflow. The Stata book is one that works fine for whatever language you're using. An ethnographer I know is using it. She's like, ignore all that Stata stuff, which is worthless, but the other part's helpful for organizing. My research team, follow it, make some decisions. At some places, I've had student groups get together and they start working through and kind of come up with procedures and kind of talk them through. This is something that's very social, coming up with workflows. Here's how I'm thinking about doing it. Let people react to it. Does it work? How's it going to work out for you? As you go forward, BITS is a great place to go. They've got all kinds of resources and links to things. The book by Christensen, Fries and Miguel. It does a nice discussion of a lot of the literature on replication in particular. There's a lot of technical material which really isn't essential. That is, they'll do some mathematics for the different models. My workflow book. This summer there's a workshop at ICSR, but it's canceled. Project Tier is a great place, particularly if you want to introduce any of this into your undergraduate class. They have a whole set of methodologies they use for teaching intro to statistics. I've met some of their students. It's really amazing. They do a great job. All right. I want to give people a chance to stretch here. And the next part that I want to talk about is basically ways to compute to get reproducible results. It's basically, you all run script files. It doesn't matter if you're doing R, Stata, SPSS. This isn't Stata centric. Kind of about the steps you want to use for computing more efficiently for reproducible results. Okay, so how many minutes?
7 to 10.
7 minutes.
Okay.
7 minutes, yeah.
7 minutes. Thanks a lot.
Okay. Yeah.